Welcome. Let's solve Leetcode 2127, maximum employees to be invited to a meeting. All right, let's make this thing bigger so we can read it. Okay. All right, so this problem is hard, and I agree. So let's try our best. So a company is organizing a meeting and has a list of N employees waiting to be invited. They have arranged for a large circular table capable of seating any number of employees. The employees are numbered from 0 to n-1. Each employee has a favorite person and they will attend the meeting only if they can sit next to their favorite person at the table. The favorite person of an employee is not themselves. Given a zero-indexed integer array favorite, where favorite I denotes the favorite person of the ith employee, return the maximum number of employees that can be invited to the meeting. Okay, so let's go over this example here. So in this example, favorite is a list of size 4. So the person at the 0 index wants to sit next to person 2. And you can see by the diagram that has taken place. The person at index 1 also wants to sit next to person 2, and that's also taken place. And the person at index 2 wants to sit next to person at index 1. So, okay, and then person 4 also wants to sit next to person 2. However, if that were to take place, that wouldn't achieve the maximum number of people. So one thing I want to point out here is that nodes 2 and nodes 1 are people, or the people at 1 and 2 are mutually they're mutual friends, or they're mutual favorites. Mutual, M-U-T-U-A-L. Okay, let's go over, well, this isn't very helpful because the diagram isn't available. Well, let's try it anyway. So person 0 wants to sit next to person 1. Person 1 wants to sit next to person 2. And person 2 wants to sit next to person 0. So, well, it's possible so that it's kind of like a triangle, so this works. That's 3. And this last example, so there's 5 people. So person 0 wants to sit next to person 3. Okay, so that actually takes place here. Person 1 wants to sit next to person 0, so that takes place here. Person 4 wants to sit next to person 1. That takes place here. And the 5th person, so 0, 1, 2, 3, 4. Sorry, person 2 doesn't get to sit by anybody. This is because person 2 wants to sit, sorry, this is person 1. Sorry, person 1 wants to sit next to person 0. That happens here. Person 2 wants to sit next to person 1. But that wouldn't lead to an optimal or maximal number of people on the table. So according to them, this arrangement would lead to 4 people sitting at the table. Okay, so let's get started. I think this problem is a little bit challenging, but this may be one of the harder problems I've ever done on Leetcode. But I think we should be able to overcome it and conquer it. So let's get started. So with this problem, we're going to convert it to a graph, meaning, well, let's just get started here. So in this case here, let's just maybe map this out. So let's copy this over, and let's kind of map this out how we're going to arrange it. So in this if we look at this and convert it to a graph, we're going to say something like person 0 wants to sit next to person 2. And person 1 also wants to sit next to person 2. So we can do something like this, maybe. Sorry, so yeah, person 2, okay. So person 0 wants to sit next to person 2. Person 1 also wants to sit next to person 2. But person 2 wants to sit next to person 1, so I'm gonna add an additional arrow here. So these two people are mutual friends or are mutual favorites. And then person 3 also wants to sit next to person 2. So maybe we'll do something like this here. Maybe we'll use this arrow and put that here. And we'll put a 3 here. So this this graph orientation is the representation of this array here. So that's kind of what we're going to be using for our approach to solving this problem. And I want to make it clear that it's a directed graph. Okay, so let's kind of get started. So one thing, well, let's make this bigger. One thing that should be clear is that maybe I'll use their notes here. That's fine, we'll just use this. So we're going to be left with 2 basic, or maybe 2.5 basic formulations. Either all of the nodes are in a cycle, or not all of the nodes, but a large majority of nodes are in the cycle. And so this is a large cycle, but nevertheless it's a cycle. And so 1 wants to sit next to person 2, 2 to 3, 3 next to 6, 6 to 5, 5 to 4, 4 to 1. So this is one scenario of how friends can be, or favorites can be situated. You can have this cycle. Or you can have something like this where 1 wants to sit next to person 2, so you still have a cycle, because this is just a 2-person cycle, whereas this is what is this? I don't know, 6-person cycle. So here's a 2-person cycle. However, though, it's a little bit different, because if you notice, the ands are different, meaning this. So 1 wants to sit next to person 2, 2 to 3, and 3 to 4, but 4 wants to sit next to person 5, but 5 wants to sit next to person 4. So you have this mutual favorites that's different from this one over here. So even though this is a cycle, this is also a cycle, because it goes back and forth. It's a little bit different, because the endpoints have basically like a leading entry. So remember, we started from 1 to 2 to 3 to 4. On the other end, for 5, imagine we're starting at 7 to 6 to 5. So these are the 2 different types of formations or orientations we can have for our problem. So what we'll be doing is, what our approach will be this. We will start by examining nodes that have an in-degree of 0. So, for example, the nodes of in-degree for this problem would be 1 and 7, because nobody has them as a favorite. And then we will maybe explore every node until there are no more nodes of in-degree 0. So what do I mean by that? So in this case, suppose we're looking at this here. So we would start with this here. We'd say, okay, we want to start with, so in-degree of 0. So from this kind of situation, we'd have nodes 1 and 7. Okay, so then if we're looking at node 1, so we would go to node 2. So actually, let's do something like this instead. Let's look at all the n degrees. So this would be node 1, node 2, node 3, node 4, node 5, node 6, node 7. Let's do this instead. And so the n degree of node 1 is 0. So that maybe let's write that down. So this will be the node, and this will be the n degree. Okay. So the n degree of node 1 is 0. The n degree of node 2 is 1. N degree of node 3 is 1. N degree of node 4. Node 4 has two favorites. I mean, 3 wants to sit next to 4, and so does 5. So the n degree of node 4 is 2. N degree of node 5 is also 2. N degree of node 6 is 1. And n degree of node 7 is 0. So that should make sense. So then, as I mentioned, so we'll start with these nodes here. So the n degree of node 7. Sorry, the n degrees of value 0. So that would be 1 and 7. So what we'll do is we'll explore the neighbors of 1 and 7, but not really neighbors, because remember each node only has one favorite. So we can go from node 1 to node, well, according to this graph, we go to node 2. When we go to node 2, we actually subtract this. So this becomes, now we're going to say that's 0. Okay, so then from node 2, we're going to go, well, on the graph it goes to node 3. So we go to node 3. And then we remove this one incoming degree. So now, yeah, so that's 3. And then we go to node 3 goes to node 4. Okay, so then we go to node 4. And then we remove 1 from here. Okay. And now, so we would, well, we would go to node 5, but node 5 doesn't have an n degree. So we can just, we'd stop there. Okay. So we only continue when we reduce and the node is 0. Moving on. Then we go to node 7. So 7 has the degree of 0, n degree of 0. So then we go to node 6. Then we reduce 6 to, we take this, imagine this, we're taking this n degree and we reduce it by 1. We go to node 5. Okay, so we go to 5. 5, we reduce this to node 1. Sorry, n degree of 1. And then in a way we would be done. We wanted to check out after we explore our graph, we want to see which nodes are left with are not fully explored yet. Okay, so then we have this then. So we would know this. Actually, let's stop. Well, sorry, I'm gonna continue on. So what we should have done along the way is we should explore like maybe the depth. So we'll have a depth here too. So initially the depth will be, when I say depth, it's kind of misleading, but it's also means the like, so it could also mean number of people at table. So originally it'll be 1. So each person will be at the table. So remember now, so let's do this again. If we're at node 1 and we want to go to node 2, from 1 to 2, that would increase. So now this would become 2. And notice it's also depth because it's 1 away from, so 2 is 1 away from 1. So that's why we add another one here. Now 3, this would be what, 1, 2, 3. So this would be 3. Like the depth is 3. Remember, it's kind of like the number of people at the table. And so now this would become 4. It's like the depth. Okay, and then we would stop here. Now from 7, that's 1. 7 to 6, that's going to be 2. And 6 to 5, that would be 3. Okay, so I'm actually going to implement this so far. I'm going to implement this so far. But just as a little hint, if you notice that we can kind of like add this up, this side to this side. So this would be 4 plus 3, which would be 7. So again, that's a little like foreshadowing of what we're going to do in the future. But in any case, I just want to implement what we have so far. Okay, so let's do that. So what I'm going to do is just set the, find the, I don't want to write favorite, so I'm going to write F. And I want to know the number of nodes, so I'm going to say n equals the length of F. So this is the number of nodes. Number of nodes. Okay. And then what do we want to do next? Well, we're going to use this in degree, so let's set that up. So the in degree will equal 0 times n. And then we'll have maybe like a depth. And each value will be initialized to 1, and then we'll have n of those. Okay. Now let's compute our n degrees like we did here. Remember we computed, well, I know we reduced them, but let's compute them. So let's compute n degrees. So we say for I in range n, will n degree. Now the question is, what goes here? So what goes here? So if we're starting, for example, we're starting at index, well, what did we start with? So 0 to n minus 1. Okay. So if we're looking at this here, so right now we're at node 0, but the value there is, that has the n degree. So the value is what has the n degree. So I'm going to say something like this. F of I, that's the n degree. So I hope that makes sense. F of I, this is the value that wants to be set by. Okay, I just hope that makes sense. And now let's just print it just so we get an idea. So print f n degree, and let's print it out. And in order not to get an error, let's just return something meaningless for now. But let's run that. Okay, cool. Let's maybe move this over. So let's kind of just, so we can look at it here. So imagine now, okay, so remember, so this was the first example here. So notice how this 1, 2, 3 people wanted to sit next to node 2. So that's what we have here. One person wanted to sit next to node 1. So this is the n degree. And then nobody wanted to sit next to, well, I don't want to say nobody, but like nobody favorited this person for 0 or node or 3. That's why there was 0 here. For a node 0, this one is a 0 and this one is a 0. Okay. So, okay, I just hope that makes sense. So why do we do that? Okay, so why do we do that? So remember, the reason why we found this is we want to know, once we have that, we know the nodes that have an n degree of 0, we can start with those nodes, and we can explore every node until there are no more nodes of n degree 0. Okay, so that's why we wanted to start with, like, for example, we know node 1 and node 7 have n degree of 0, so we would explore as far as we can to find their depth. So let's do that. So let's find that depth. So what we'll do is we'll use a double-ended queue for that. So we'll say, okay, so let's find the nodes that have an in degree of 0. So for I in range n, if in degree of I equals 0, and we're going to say I, and then we're going to use this double-ended queue, and this will be q. And this is just a shorthand way of building our double-ended queue. Then next, well, let's print it out. Let's just print out our queue. Okay, let's do that. Okay, so okay, this should make sense. Node 0 and node 3. Did I not print it out anymore? Oh, I should have. Probably should have just left it here. Print in degree. So we see that node 0 and node 3 have nobody favorites them to, like, nobody requests to sit next to them. So these are the nodes we would start with. Okay, so now let's do it. So let's explore. So visit all nodes to find their level or find their depth. So remember, what we're doing is we want to find how far away these other nodes are. We want to find, and by doing that, when we say depth, we're really saying like the number of people at the table. So for example, this is one person at a table. If I go to the next one, that's 2 people at a table. This is 3 people at a table. This is 4 people at a table. So again, that's kind of what it means. So it's kind of synonymous. Okay, so let's begin. So we'll say while q, and then we'll say node equals q dot pop left, and then we'll say we'll get the neighbor. So then this is the person we want to sit next to. So we say f of node, and then we say, okay, we're going to say the in degree of this neighbor. We're going to subtract 1 from it. So we're going to subtract 1 from it, and then what do we do next? And then we'll adjust the level. Okay, so that's something that we didn't. Oh, sorry, or the depth. So we can do that here. So we're going to say the depth of the neighbor will be 1 more than the depth of the current node. I'll leave that here for now. I do have a hesitancy about this, but for now I'll leave it. I think it's okay. But I think it's okay, but I just had some doubt about it. Maybe I'll explore it later. But in any case, it's fine for now. And then, so notice here we reduce the in degree by 1, and we're going to check by doing that if the in degree of the neighbor, if it's 0, we'll add it to our queue. So we'll say q dot append all neighbor. Okay, then we'll print our queue again. So let's print our queue again. So we'll print the in degree. Print the in degree. In degree. Okay, so then let's print that out. Okay, so originally our in degree was this here, 0, 1, and 3, and now it's 0, 1, 1, 0. Okay, so it's kind of like what we did over here. Remember, when we originally the in degree was not this, but as we traversed through our graph, we ended up with this here. So I just wanted to point that out. Okay, so what do we do next? Okay, good. So this is, so we know we have we know what we have. Okay, so let's go over what we have. So we're left with this situation. Okay, so let's go over that. What does that mean? What does that mean? Okay, so what we'll do is, so now we're gonna, so what do we do next? We will, what we kind of know is we know that we have cycles left. This is a cycle. It's a cycle. So we will explore the remaining cycles. So when we have cycles, they'll either be of size 2 or bigger than that. So either we'll have maybe we'll have 2 cycles, or we'll have like when I say 2 cycles, I mean you know, hopefully you know what that means, or that means like just two elements, or we'll have or greater than that, or greater than 2 cycles, greater than 2 cycles, greater than length. Let me see, length 2 cycles, greater than length 2 cycles. So something like this is 4 and 5 is considered a length 2 cycle, but something like this here would be a length 6 cycle, because there are 6 elements or 6 nodes in the cycle. So I want to make that point clear. So now the question becomes, well, when we have these, let's make this. So when we have these length 2 cycles, what do? Well, we can do 2 things. What we want to do is we want to know, like, for example, we'll know this node and this node. So like we'll know its favorite. So what we'll do is we can say, okay, if it's a length 2 cycle, we know there's only 2. And what we'll do is we'll say, okay, we should add the depth of each of them. So in this case, we would be adding depth of 4 plus depth of 5. So in this case, it would be like 1, 2, 3, 4. So in this case, it would be 4 plus, in this case, it would be 1, 2, 3. And so I hope that makes sense. Okay, so and now imagine in this case where we were here. So we found a cycle, but it's not a 2 cycle. So, but in this case though, we would just figure out the length. So while we know we're exploring cycles. So while we're exploring the cycles, we find the length of the cycle, and when we explore this cycle, we'll find that it's 6, and then we can just compare it. So for this guy, we'll say, let's do this here. So when we find some of the length of cycles, we'll just say, okay, we will compare the length of this cycle to the maximum cycle, or maximum length so far. Okay, cool. All right, so I hope that makes sense. All right, so let's continue on then. All right, so here we are. Okay, so now what do? So we'll store maybe our longest cycle, and it'll be 0. And then we'll have maybe 2 cycles. 2 cycles. Okay, so let's move on. So let's continue on. So we'll say for I in range n. Now we don't want to explore the nodes that are already 0. We don't want to explore them. Like those are not going to lead to a maximal result. We want to explore these guys. So what we're going to do is we're going to skip those. We're going to say, so if I guess maybe the n degree of I equals 0, we just continue. We don't need to explore that. We want to explore the ones that are not. Well, let's maybe put this down here. We want to explore the nodes that that do not have that are part of a cycle. Okay, so we'll say, okay, so the cycle length, this will be the current cycle length, and it'll be 0. And we'll say what to store where we start. So let's store where we start. So for example, we'll start, if we're starting here, we'll start at 1, and then if we eventually reach it, we know it's a cycle. And kind of like the same thing here. We will store where we start. So let me just store that really quickly. I'll just say maybe we'll call this the current, so we don't override where we start from. And now we just explore. So for example, if we're here, now we'll just explore as far as we can. We know we're in a cycle, so we're going to explore as far as we can. So we'll do this here. So we'll say while in degree of current is not equal to 0. So while we're exploring our cycle, if we explore a node, we'll reduce the in degree. We'll reduce the in degree. So that's a way of keeping track of if a node is visited. Okay, and then so let's do it. So say, okay, in degree current, and we're just going to set it equal to 0. We can set it equal to 0, and then we'll say now we'll add to the cycle length, and then we'll say current now equals the neighbor of current. Okay, so imagine we were doing this here. So we're at 1, we go to 2, we go to 3. So as we move along, we're adding 1 to our cycle length, and then eventually, though, notice though how these in degrees all get reduced to 0, because right now all the in degrees are 1. But once we move along, we reduce them to 0, and then that's how we exit here. So remember, that's how we exit here. Okay, so once we exit, what do? Well, we compare. We want to check if this cycle length is a 2 or more than that. So if we found a 2, we want to add the depth from each side. So let's do that here. So if we find if the cycle length is 2, then we say, okay, we say the two cycles equals the depth of the start, and the start was I, right? So we started at I. So depth of I plus the depth of the current one, depth of the current. So that's if we had, if we were here. So imagine suppose we started at node 4, and we're here at this block of code. So we would go to node 5, and then we would break immediately, and then we can just add them. Otherwise, so we know it's not a 2 cycle. So then we say, okay, otherwise we say we're going to say longest cycle equals the max of the longest cycle, or this cycle, or whatever this is, or the cycle length. Okay, and then what else? Then I think we would just return the max of the longest cycle versus 2 cycles. Okay, so let's take this off. Now let me go over something real quick. So if you notice what we have here, we have this. Now let me ask you a question. Suppose we have this here now. I have an 8 and a 9. Could we put this all on a table? So I know previously we could put this in a table, but could I also add this to the table? And yes, we can. So just it's hard to well, let's try it. I think we can make a circle out of this. Maybe let's do this. Maybe 4 to 5. I think we can. Let's do it. So my point to you is this: notice how we're adding the 2 cycles. So notice how we're adding it here. So this is why it's okay to add the 2 cycles. So this is a 2 cycle and this is a 2 cycle. So let me just make a circular table out of this, so maybe it's easier to visualize. Maybe so. Let me do. Let me see. I think yeah. I'm just gonna do this here. I think it'll be all right. Let's try this here. Let's copy you. Actually, I don't think we even need to do that. Yeah. Yeah, okay, I'll just do it. Let's try it. So let's put you, so let's take this 1 off here. Let's put this 1 down here and put that arrow here. Okay. And then that's okay. And then maybe put this 7 over here. Put this 7 here. And put you here. Okay, so imagine this is our table. So these all, none of these are affected. So if we put this 8 and 9 in here, like we squeeze it into this table here, like it doesn't affect, like 1 and 8, they don't affect each other, and 9 and 7, they don't affect each other. So my point to you is that that's why we added, that's why it's okay to just add it. Whenever we see the 2 cycles, we can push them together, because, you know, or just imagine something like this on a more simpler case. What if we had something like 1 wants to sit next to 2, 1 to 2, and then 3 and 4 want to sit together, and then 5 and 6, and then 7 and 8. So you can just put all these 2 cycles together, and that's it. You can just line them all up. Well, not line them up, but like imagine a circular table. So it would be perfectly fine. So I just hope that makes sense. Okay, cool. And I just wanted to stress that why it's okay to put this plus equals here, because we can stack together the 2 cycles. It's when we don't have when we have the longer cycles, something like this, that's when it has to be closed. We can't allow for additional favorites to be inserted. Okay, well, let's test if it works. Let me comment out the comments. Okay. I think that's everything. All right, let's test it. All right, let's see where I went wrong. Did I return the right answer? Okay, that's fine. Return as longest cycle. 2 cycles, okay. And then we have, okay, this is fine. This is okay. This is okay. Depth, okay. For iron in range N. Okay, this is okay. I think this is okay. Okay, so let's try this here. Node pop left, neighbor equals, okay, that's good. That's good. Depth of neighbor equals depth of node plus 1. Okay. If n degree of neighbor equals 0. Okay, this looks good. Okay, longest cycle was 0. Longest cycle. Okay, so those are good. So then 2 cycles is 0. So if in degree of that equals 0, then we continue. Okay, cycle length equals 0, current equals I. Okay, this is okay. In degree of current equals 0, cycle length plus equals 1. Okay, current equals f of current. Okay, this looks good. Cycle length equals 2, 2 cycles plus, oh, I get it. Never mind. I get it. So this is where it's off here. This shouldn't be current. This should be f of I. That's a good question. So let's print this out here. So let's print out I, f of I, f of I, and then we'll print out current. And then we'll see why it's inaccurate. Okay. Yeah. Do you see why? So it's kind of like here. So we're at 1 and we keep exploring, but then we fail once we reach our self. But what we should do is, once we reach our self, we want to go to the like, for example, once we reach our self, like 4 goes to 5, then 5 goes to 4. So once we reach our self, we want to say, okay, if you're a 2 cycle, we just want our favorite. So in this case, we know we're 2 cycle, so I and current are the same at this point, but so we should just do this f of I. Okay, then that'll fix everything. Let's test it now. Good question. Okay, great. Let's submit it. All right, looks amazing. All right, I know this problem was hard. This video might be maybe my longest, and I apologize. If you have any more questions, or it was still complicated or difficult to understand, I apologize. Either leave me a comment and I'll try again, or maybe even I'll make another video if you so desire. But I recommend just kind of sleeping on it and studying it, and hopefully it'll come slowly but surely. Okay, if you found this video helpful or beneficial or educational, please consider liking or subscribing, or both. Other than that, have a wonderful day. Take care of yourself. Cheers.